So first things first is I have a graph of a function. This function is a quadratic, right? This is an x squared graph. Do we agree? Okay. We are trying to figure out what is the derivative of this function, okay? So to get us there, we're going to figure out a few points, and we are going to look at a slope that is close to that point, or on that tangent, okay? And what is that output going to give? And then we're going to graph them in the second one, okay? We're going to estimate, but we are also going to do one of them by actually using our limit definition. Okay, not limit definition, our definition of a derivative, okay? So what I'm going to do is I'm going to zoom down in here. We are going to evaluate using our definition of a derivative at point 2, okay? So we are going to say the limit as h approaches 0 of my function is x squared, so I am plugging in not x plus h squared. I'm looking at a specific point. So I am plugging in x plus, bless you, 2. Okay, I'm looking at a specific point. So x plus 2 minus f of 2, right? We're going to plug that into my function, all divided by h. That is my definition of a derivative, yes? At a point, okay?
Sure, we'll go with that.
Now we're going to plug in this x plus 2 piece. We're plugging it into the function x squared. So this becomes x plus 2 squared minus, plug in 2, I get 2 squared, okay? I'm dropping the limit piece for now. We will bring it back in at the end when we are evaluating it, okay? This is all divided by h. Oh, wait, hold on. This x should be an h. My bad.
What?
Otherwise, this wouldn't work. My bad. Okay. Sorry, guys. Okay. So now I'm going to take that x plus 2 and I'm going to expand it. So x plus 2 times x plus 2, you could write that out, or we know that this is going to be h squared plus 4h plus 4. I just FOILed that out, okay? And then I've got minus 4 at the end, yes? All divided by h, okay? I can get rid of positive 4, negative 4. So now I am left with h squared plus 4h divided by h. And now what can I do? Yep, one of those h's comes out of all of those, and I have h plus 4 divided by h. So now we're going to bring that limit statement back in, and I have the limit as h approaches 0 of h plus 4 is equal to 4. Right? If I plug in 0, 0 plus 4 is 4, okay? So what this means is at the point 2, right, at the point 2, I have a slope on my tangent of 4, okay? Let's look at the actual picture. At 2, I have a point here. Where is that y value at? Positive 4 as well. Okay, that is not always going to be the case, that it is also the derivative. If I were to try and sketch a line that is tangent to that point only on this graph, it's not going to be perfect, but do we kind of see here on the bottom, it's a little bit better. I have kind of another point here, right? And that's my slope. My slope is 4. At that point, if I were to take a ruler and make a line on that point without touching any other point on the curve, it would have a slope of 4 for that line. Does that make sense? That's how that's like the same thing as doing it analytically using my definition of a derivative, okay, that we did last class. So we are not going to do all of them like that because that would take us way too long, okay? We now need to just kind of look at the graph and figure out what is my slope going to be at that tangent point. Okay, so at 0, 0, 0, right? My y value is 0. If I were to draw a tangent line at this point, what is my slope of a horizontal line? 0. Okay. I'm going to look at the point 1 now. Oh. Okay. The point 1 is also at 1. And if I were to think about drawing a tangent line here, just only touching at that point, okay, with a straight line, it's not perfect, but what is our slope approximately there on my pink line there? Like 1.5-ish maybe? 1.5, 2-ish, yeah? Now at -1, my y value is also at 1. Use what we know about a parabola. Parabola is symmetric, right? Across that x-axis or y-axis there. So that means my slope at -1 is also going to be what? Yeah, -1.5/2, right? So -1.5 or 2-ish, okay? And lastly, at -2, our y value is also 4 of our quadratic, which we already found this one analytically. On the right side, our slope at our slope at -2 is 4. No, +2, sorry. So our slope at -2 is also what? Yeah, it's -4, right? Okay, so I'm going to take all of those values of our derivative, and I'm going to bring them down to our next function, okay? Because we are going to graph the derivative function of f of x equals x squared, okay? So I'm going to write these values down again. I've got 0, 2, or 1.5/2-ish, and 4, -1.5/2-ish, and -4, okay? So this is my derivative graph. Derivative. Okay, f prime of x stands for our derivative. So now I'm just going to plot these points. It's the same x value, except for instead of plotting a y value, I'm plotting the derivative of our original function, that value. So that slope at that point. Okay, so 0, 0, easy one. 1, I'm at 1.5, 2. 2, I'm at 4, that's 3. 2, I'm at 4. And then -1, I'm at about there. And -2, I'm about there. Okay?
Wait.
What?
1.5 divided by 2?
No, like /2. It couldn't really tell perfectly. It's like 1.5 to 2-ish. Because we were just estimating on that graph. Okay? So this, very, very closely, it's just off by a little bit, is what kind of function? It's a linear, right? It's a linear function. So this is a line. Our original was a quadratic. Okay, our original function was x squared. If I were to write the inverse function, not the inverse, I'm sorry, the derivative function, if I were to write this equation of this line, what would it be?
Parabola.
No, the equation of this line. How would I write the equation of this line right here?
Y equals x.
Y equals x, but it's actually a slope of not just 1, it's a slope of 2-ish, right? Okay, so my original function is x squared. My derivative function is 2x. Do we see maybe a relationship between those two and where they came from? Yes? A little bit? Okay, good. Because on the next page, we're going to do x cubed, okay? The next page here, I have a function that looks like this, okay? This is a cubic function, right? If this was actually centered at 0, 0, our cubic function is x to the third power, right? I know it's not quite centered at 0, 0, but just for ease of trying to find the derivative right now, I want you to try and guess using what you just saw of finding the derivative of a quadratic. Make a guess of what your derivative function would be if your function is x to the third power. So make a guess. If it's totally wrong, that's okay. But let's guess and see what we think the derivative function is going to look like. Okay, write something down. I don't care if it's wrong. All right. Go ahead and shout out what answers you had.
3x.
Did everyone have 3x? Okay, let's see if we're right. All right, here we go. We're going to do the same idea. We're going to choose, it says choose the best points on the graph. Make sure you are choosing points that go from increasing to decreasing and vice versa, okay? So talk to the people around you at your tables. What points would be really important to have on our graph? Okay, looking at increasing, maybe constant, zeros, all that kind of stuff. What points should you maybe choose for your x? Okay, just talk about it real quick. Some values that I would choose, do you have a question? Some values that I would choose is specifically when we have a change between increasing and decreasing. Okay, do you see that value? So we're going to look at specifically x equals, what is that, -4, and x equals 2, okay? Those two values, my outputs are 10 and 2, but my derivative at that value is what? What is my slope at that point that is tangent? 0, okay? Okay, some other points that we probably should choose. Maybe some positive slopes. So maybe you chose a point like -6. Or if you chose, I just chose -6 because it crosses at a nice value there. But you could have chose -7. That also kind of crosses about there, okay? To find the slope at that value. So I'm going to choose -6. That is a value of 6. And my slope, if I were to try and draw a tangent line to this at -6, hold on. It is kind of hard. If you had like a ruler, it'd be a little, oh, I didn't do a great job there. But it is close to like 3.5 or 4-ish, yeah? Let's say like 3.54-ish. Okay. Another positive, if I went over to +4, this crosses pretty nicely right there, right? That's going to give us a positive slope. If I tried to draw a vertical, or not a vertical, but a tangent line here. Kind of same idea. It looks like about 3.5-ish and 4 for my slope. But my y output is still 6, right? Okay, and then we probably need one more point. Where's that one more point probably need to be? At 0? Yeah, we could do 0. At 0, we want the point, or the slope. So I've got at 0, my slope, no, my y value is 4. And my slope at 0, let's see here. We could go on the other side maybe a little bit better, actually. Yes, it is tangent at this point. It's just kind of hard to show. It looks like, if I zoom in there, it looks like it's about maybe 1.5. Yeah? You guys kind of see that? Huh?
Wouldn't it cross at the top?
But it's just like tangent at that point.
Oh.
Like, yes, I see what you mean. Yes, technically if you draw it and it would continue, yes, but it's only tangent at that point. Because otherwise it's just going through that line. Okay?
I want to see what like.
Yeah, so like negative.
It's down 2 over 1.
Yeah, you're right. Let's go -2. Okay? -2. All right. So we've got some values of when we have zeros. Okay, that means it's going to cross our x-axis on our derivative function. And we've got some positive and some negatives from when it was increasing and decreasing. So I'm going to take these values and I'm going to rewrite them down below. I'm going to write my x's first. And then I will write my y's. Or my inverse. Not my inverse, my derivative. I'm sorry. That's what you get for teaching pre-calc and calc. Okay. That's supposed to be a 3. And -2. Okay, so we're going to plot these points on our derivative graph. Okay, -4, 0, plotting a point. 2, 0, plotting a point. -6, 3.5, and 4, 3.5, 4-ish, and then at 0, we are at -2. Okay, what kind of shape is this going to be? It's a parabola. Oh, I totally missed that one. Okay, this is a quadratic. So my original function, remember, if it was centered at 0, 0, is like x to the 3rd power. My derivative has to have an x squared in it. So a lot of you said it was 3x. Would you like to change that to be something different? Maybe with an x squared? Yeah? So this is my derivative of my original function of x cubed. Okay? Okay, so this is your first derivative shortcut. This is called the power rule, okay? These are shortcuts for what we were just doing. Okay? Basically, it says if I have a function that is something raised to a power, hence why it's called the power rule. Okay? What you are going to do is this little dx thing, that stands for finding the derivative with respect to x. Okay, so anytime you see dx, that means you need to find the derivative with respect to x. Okay? And the derivative of our function of x to the n power is n in front. So you bring the power down. And then we have n minus 1 in our exponent, which means we are subtracting by 1 power. Okay, so we originally, on our first problem, remember, we did the derivative of x squared was 2x, right? Brought it down in front, subtracted 1 from the exponent, right? The next one we did was x cubed. X cubed, bring that down in front, subtract 1 from the exponent. Okay, so being able to find the derivative quickly, now if I wanted to, I could plug in my values in for x here, because this is my derivative function, right? And I could find out what my slope is at that point. Okay? Awesome. Anytime you also see the word differentiable, okay, that means you can take the derivative of it, okay, if it is differentiable. All right. Let's look at a few examples here, okay? We already did example A, okay? F of x equals x to the third. Again, look at your notation here. If I'm written in f of x function, we want to write our derivative as f prime, okay? So if I have x to the third, I bring down that 3, and I have 3x squared. Or 3x to the 3 minus 1, which is 3x squared. Okay? Letter B, I have y equals, so in my answer I'm going to have y prime, okay? If I rewrote the square root of x, could I rewrite this as x to the 1/2 power? Yes? Okay, so this 1/2 comes down in front. I have 1/2 times x to the 1/2 minus 1 power. Well, what is 1/2 minus 1? Negative 1/2, so this becomes 1/2 x to the negative 1/2 power. Okay? So this would technically be appropriate to leave on your test. I would accept this. I would also accept it, well, I wouldn't because I'm not the one grading it, but the AP test would also accept this if you left this as your answer. On your circuit worksheet that you are going to have to do, you might need to move things around in order to have positive exponents. So let's just kind of practice that here since that's what you're going to see on your homework tonight. If you have any negative exponents, they move to the opposite side, right? So this actually becomes 1/2 times x to the 1/2, which you might see as 1/2 times the square root of x. Okay, this one right here, finding the derivative of the square root of x, and that equals this function right here, that is going to be one that you are going to want to memorize, okay? That's probably going to be one that I'm going to have you guys put on your notes, either next class or the class after. Your note cards, sorry, okay? So you're going to want to memorize that derivative. There's going to be a bunch of derivatives that you are going to have to memorize, so our note cards are going to get even larger here soon, okay? All right, next one. I've got 1 over t to the 4th. Can I rewrite this as t to the negative 4th power? Yes? All right, try this out. Try finding the derivative of your function g. All right, did we all get negative 4 over t to the 5th power? Yes? Okay, moving on here. We're actually going to skip letter D for right now, and let's look at letter E. Okay, letter E, if I wanted to rewrite this in terms of a fractional exponent, this would be the same thing as x to the what power? 3/4. Okay, so go ahead and try and find the derivative of this function. Okay. All right, I'm bringing down this 3/4. I've got times x to the negative 1/4 power. Again, if you wrote this on a test or an AP test, this would be fine. However, on your circuit worksheet, it is going to have it with positive exponents only. So if we rewrote this, this would be 3 on top, 4 goes on bottom with my x to the 1/4 power, bless you. Or we could have 4 times the 4th root of x. Same thing. Okay. Wonderful. Okay. Now, let's think about a straight line. If I looked at a graph, right, and I had a straight line, horizontal line, what is my slope of that horizontal line? 0, okay? So if I have a function, y equals 5, for example, in part F here, if y equals 5 is a straight line, my derivative tells me my slope, right, at that point, or of that line, right, which would be just 0. Right? My slope is 0. So if you have a constant, the derivative is 0. Technically, you're doing the same thing. Really, there is no variable here, so we could think about this as being 5x to the 0 power, right? And if I followed the power rule, this is what happens. 5 times 0, x to the negative 1 power. Well, what's 5 times 0? 0. So this goes to 0. Okay, so it's still technically following the power rule, right? However, there's no variable there. Okay, so your derivative of a constant is 0. Even if I had like g of x, let's say g of x was equal to 3 to the 5th power. Would this become 5 times 3 to the 4th power? No, this is just a number, right? So this derivative would just be 3 to the 5th power. Okay? All right. Constant multiple rule means that if I have a derivative, or if I have something, a function that is differentiable, right? I have some number times a function, okay? I can think about taking that number out and multiplying it by your derivative, okay? So if I look at example A, this is really the same thing as 2 times x to the 7th, right? So in this example here, 2 is technically my c value in this, and f prime of x, this is what I need to take the derivative of, right? Okay, well, if I bring that 7 down, what am I going to do with that 2 and that 7? Multiply them together. So this becomes, y prime is 2 times 7, x to the 7 minus 1 power, or 6th power, right? So this becomes 14, x to the 6th. Okay. Let's rewrite letter B here. This is the same thing as 3 times x to what power? Negative 2. So I'm going to bring that negative 2 down in front. So this becomes 3 times negative 2 for my derivative. And this is x to what power? Negative 2 minus 1. Negative 3. Okay. So my derivative is negative 6 x to the negative 3rd, or on your circuit you would see probably negative 6 divided by x to the 3rd power. They mean the same thing, okay? This answer is appropriate on your AP or test in my class. This answer is what you would see on your circuit worksheet today, okay? All right, letter C, I've got the 6th root of x to the 5th. How could I rewrite that as an exponent? X to the 5/6. Yeah, times 1/8. So I'm going to put a 1/8 in front of that. I think that'll make our lives a little bit easier here. So This 5/6 comes down in front, right? So this becomes, for my derivative, 1/8 times 5/6 times x to the 5/6 minus 1, which equals negative 1/6. A lot of sixths, a lot of fractions going on. So multiply our fractions, multiply across the top. So this becomes 5 divided by 8 times 6 is 48. X to the negative 1/6, which again would be fine on a test or AP test. However, on your circuit worksheet, your answer would show up as such. It would be 5 over 48. Yep, x to the 1/6 or the 6th root of x. Okay, either one is fine. This is just extra practice of applying the power rule. If you would like to try it out, you can. It is not homework though. I feel like we feel pretty okay about it, and I want you guys to get some time maybe to work on your homework. So we'll see how that goes though. Okay, next page here. This, I'm going to do just parts A and B here with you. We are going to skip C and D because it's the same idea. If we have parentheses, right? I've got this parentheses, 3x to the 4th, there's no parentheses, right? So I can do my power rule. This is the same as 3/8 times x to the 4th, right? So bring that 4 down. This becomes, my derivative is 3 over 8 times 4, x to the what power? To the 3rd, okay? Which if I multiply across, this is 12 over 8, x to the 3rd, which you could write as 3 over 2x to the 3rd power. Okay, you could rewrite this also as 3x to the 3rd on top and 2 on the bottom. That's fine as well. Now, letter B, the only difference here is we have parentheses, right? So that means this 4 is technically going to both things here, right? So let's rewrite this as 3 to the 4th power times x to the 4th power, all divided by 8, okay? Now, what is 3 to the 4th power? 81, yes. 81. So I've got 81 x to the 4th divided by 8. This is what I'm taking the derivative of, okay? So I am going to bring that 4 down. Before I multiply it, let's just write it there for a second because I think some things are going to simplify here. And divided by 8. Now, if I have a 4 on top and an 8 on bottom, what do I have now on the bottom? 2. So your final answer here for your derivative is 81 x to the 3rd divided by 2. Okay, do we see how similar problems, totally different answers? Okay, cool. Now, this last little rule here is basically just taking our idea of the product rule and putting a bunch of product rules together in one with either addition or subtraction, okay? This fancy notation just says that we are taking the derivative of when we're adding our functions together or when we're subtracting our functions, and all we get is the derivatives added together or subtracted together, okay? That's what we call the sum rule and the difference rule of derivatives, okay? So if I look at example A, we're not going to do all of these, but if I look at example A, I have 1, 2, 3, 4 functions there, right? I am finding the derivative of each one of those and then keeping whatever sign is there. So if I take the derivative of this function, for this one here, I would move that 3 down in front. So this becomes 4 times 3, x to the what power? 2nd. Okay, now I'm going to derive the negative 5x squared. So I move that 2 down in front. This becomes negative 5 times 2, x to the 1. Okay, if I take the derivative of 7x is raised to the 1st power, right? So I technically bring down that 1. So it is 7 times 1, x to the 0, right? And what about 3? What's the derivative of 3? 0. So I don't need this one. I don't need to write the derivative of that. Or if you want to put 0, you can. But now we can simplify this, right? This becomes now 12x squared minus 10x plus 7, because x to the 0 is really 1, right? And then we're done. That's your answer. So you find the derivative of each individual piece, and then you just add or subtract them all together. Okay? Cool. Let's look at letter C. You might have to do some algebra before we can actually find the derivative of these things. Okay? So right here, we can't just only distribute that or like do the power rule of x squared. We have a whole function here, really, which means I have x squared times x, which is x to the third. I have x squared times negative 3, so minus 3x squared. And then I've got plus 1x and minus 3. Okay? So really, I am finding the derivative of every single piece that is shown here. Okay, so when I take the derivative of x to the third, we get 3x to the second power. Okay, take the derivative of negative 3x squared. What am I going to get? 2 comes down, so I have minus 3 times 2, x to the first power, right? For my 1x, I've got technically to the first power there, so technically it's 1 times 1, x to the 0 power. And then what is the derivative of just a number? 0. So this would give me 0. Okay? And if I simplify this, I get... That's exactly right. And I don't need this 1x to the 0 piece because x to the 0 is 1, right? So 1 times 1 is 1. So your final answer here is right there. Okay? Now, you might see other things like B, D, and E on your circuit, okay? Do some algebra first before you actually start taking the derivative, right? Like for letter B and E, we have dividing by things. Did we ever talk about a dividing rule? No. Okay, so you can't use anything like that. So I need to rewrite this basically as x to the third minus 4x plus 5. That's all being multiplied by x to the negative 1 power. Do you agree? Okay, so rewrite it, and then you can have it and take your derivative of each piece using the power rule, okay? So try out your homework. Let me know if you have questions. Your answers should all be on there.